Right, so we'll start. Good morning, everybody. Let's start from the yesterday's. For the previous contest, the easiest task for the previous contest as a warm-up. So this will be task couriers. So most of you had this task accepted, but because we have at least two different approaches for this task, I think it will be useful to talk a little bit about this task. So basically, you have a sequence of numbers, and you have some queries to answer. Each query is talks about a segment from this sequence. So, for instance, we can ask about such segment, and the query is as follows: you have to find a number in this part of the sequence, which occurs at least half of the times. So, for instance, here, if we have a segment of length 5, we need to have at least 3 occurrences of some number. So for instance, here the number 5 occurs more than a half. So this will be the answer. Number 5 will be the answer to this segment. If there's no such number, you just answer 0. So for instance, for this part, no number occurs more than a half. 5 occurs like exactly 5. So for this part, the answer will be 0. So this is a known problem. The name of it is finding a leader in the sequence. But here we need to find leaders for smaller parts of the sequence. We have multiple queries. So this is finding a leader in a sequence, and there are for one sequence there are actually several ways to do this. For instance, you could just calculate, like iterate over this part of the sequence and counting each number on a map or something like this, and then you can just take the number with most occurrences and test whether the number of these occurrences are at least half the length of the segment. Another approach is to just sort the numbers and take the middle one, because if there is a leader in the sequence, then like the median of the sequence will be the leader. So, of course, if you want to know the median of the sequence, you don't have to sort. You can use like the linear algorithm for finding the median. For instance, nth element from C++. This will give you the linear time to finding a leader in some part. Of course, for us, it will be too slow because we need to do this. If we do this linearly for each query, it will be definitely too slow. But it's good to recall one more algorithm for finding a leader in the sequence, because it will be we can then adapt this algorithm to when we will building a binary tree over this sequence. Because usually, if you have some queries about some segments of the sequence, it's usually you can find out some kind of a solution for when you're building a binary tree, some segment tree over this sequence. But then you have to like find a way to store the information about different ranges of the sequence. So another algorithm for finding a leader is as follows. You are just you have to make one nice observation. So let's say that you have some segment here, and let's say that you take two numbers which are different in this segment. So for instance, let's say you take 3 and you take 5. And what happens if we erase these two different numbers? So then we get a smaller sequence without two elements. And there's a nice property that if the bigger segment has a leader, then the smaller segment, like without these two different elements, will also have the same leader. Because basically what we've done here, because these guys are different, so we removed at most one element which was the leader. So actually, if the leader occurs more than half in this bigger segment, it will occur more than half in this smaller one. So basically, what we can do, we can just like iteratively remove different elements from this segment, and it's nice to do this on the stack. So we will maintain a stack, and we will put the numbers on the stack one by one. And every time on the stack you have, on the top of the stack you have two numbers which are different, you just erase them from the stack. So on the stack we will have like 5, then we will put 3, and these guys are different, so we can just erase them. Then we will put another 5, another 4, put 4, we can erase them, and then we will have 5. So for instance, for this part, we would have 5, then 1, erase them, and 2, and erase them. Okay. And for instance, for this part, we would have 1, then 2, then we can erase them, and then we will have 5. And basically what we are saying here is if we have some number at the end of this process, if you have some number on the stack, this will be the candidate for the leader. So basically, if a sequence has the leader, this must be this number. So for instance, here we see that this is actually the leader. For this, in this example, we had no elements on the stack, so we know that there's no leader in this segment. In the third example, we have 5 on the stack, but the problem is that here in this part, 5 is actually not a leader. Here the answer is 0. So recall that we say that if the segment has a leader, then the number which is on the stack is the leader. But we can have some number on the stack, but actually it's not a leader in the segment. So after we find a candidate for the leader, we still need to have to check whether this is a real leader in the segment or not. But actually, if we have one candidate, so if we are answering a different question. We are not answering the question, what is the leader in the sequence? We are just answering whether the certain number is the leader in the sequence. And if we have this candidate, it's quite easy to calculate the number of occurrences of this number because we can do some kind of prefix sums for all of the numbers. The number of so basically, as we did in the task about difference, we just for every number we can store the positions of this number in the array. So we can say that we have a vector of positions. Like for instance, for number 5, we know that its positions are 3, 5, 7, and 8. So these are like 3, 5, 7, and 8. And we can do binary search over this array. So we can binary search over the beginning of the segment and for the ending of the segment. And we have 2 pointers there, and we can just like calculate the difference of these pointers to get the number of occurrences of 5 in this segment. So basically, this algorithm will give us a candidate for the leader, and then we have to test whether this candidate is a real leader or not. So testing basically boils down to just binary search. So it is like log n if we know the candidate. But unfortunately, like this algorithm still needs a linear time to go through the whole whole segment. So still, it's a linear time for finding the finding a leader. But this algorithm has a nice property. If you look a little bit closer at this algorithm, you see that you don't have to maintain you don't have to maintain the full stack, because if there are some numbers on the stack, all of these numbers are the same. So let's suppose that we have like bigger example. So we have like 1, 5, 6, 5, 5, 5. So this will be like a segment which definitely has a leader 5, and we will, if we go through the stack here, we will put 1 and 5, and then we erase them. Then we will put like 6, 5, and again erase them, and then we will put 5 and 5, and let's say that this is also 5, and here we have 2. And we will put another 5, and then we will put 2 and erase them, and then we will put another 5 and 4 and erase them. So every time, because every time we see 2 different numbers, we erase them from the stack. So actually, all of these numbers in the stack are the same. So you only need to remember the number of these numbers. So actually, you don't need to remember whole stack. You need to remember only value and like number of occurrences in this value. So let's say this is kind of a multiplier. So how many of these values are here? And at the start, the multiplier is 0, and the value is like, it doesn't matter. And we go one by one. So we look at 1, and then we put here. So the value will be 1, and we have one element of 1 here. And then we encounter 5, and we see that 5 is different from this value. So basically, it boils down to remove. We will remove 5. So we will just not put the 5 to the stack, but we will remove also one element from the stack. So this is like just decreasing this value of. So let's say maybe this is like a counter. So this is the decreasing the counter. So then we gain 6. So because the counter is 0, so actually the stack is empty. So we put a value on the new value on the stack, and we put the counter to 1. And once again we have 5, so we just decrease the counter. Then we put 5. So again, stack is empty, so we can put a new value on the stack and increase the counter. Then we have another 5. So it means that this 5 is the same as the number on the stack, so we just increase the counter, and another 5 increases the counter. Now element 2 decreases the counter because it's different than 5, and another 5 increases the counter, and 4 decreases the counter. So at the end, we know that we have 2 values of 5 on the stack, and 5 is the candidate for the leader, and we can test it using the prefix sums. Okay, so what do we have here? So actually, we know that after like visiting some prefix of the sequence, we can like compress all the information about this prefix into these two numbers. So basically, we have like constant often information about the whole prefix of numbers, and this information is enough for us to actually add new numbers to the sequence. And basically, this will be the basis of our algorithm using segment tree, because it turns out that this information is enough. It's enough to if we have two parts of this of the sequence, and for every part we have this information, we can in constant time merge them into one sequence and also produce this kind of information for this whole sequence. So, for instance, if we have some values, so this is one part, and for this part we have value 1 and counter 1, and we have another part, and we have value 2 and counter 2, and we would like to produce from them the information about the merge of these two parts, and produce value and counter for the whole sequence. So basically, this means that we can try to like simulate what will happen with this algorithm, because and it turns out that we have several cases here. So one case is that these two values are actually the same. So here we have some candidates for the leader. In this part we have a candidate V1, and this part we have candidates V2. So if these candidates are the same, so basically this is the candidate for the whole sequence. So if V1 is equal to V2, then V is the candidate for the whole sequence, and what is the counter for this candidate? Yeah, it's the sum of occurrences for these parts. So C is C1 plus C2. Okay. Else we have two different candidates, and actually we can think of it. Okay, we have some candidate here, we have some candidate here, and we can do once again this observation that we can remove two different elements from the sequence, and still we would end up with the same candidate. So, for instance, if element V1 is at least frequent as element V2, so we can remove elements V1 and V2 one by one, until we end up that we don't have enough elements V2. So basically it means that the candidate will be V1, and the counter for this candidate will be C1 minus C2. Yes, because we end up removing C2 pairs V1, V2 from the sequence. And we have symmetric case, so if C1 is less than C2, then the candidate will be V2, and the counter will be C2 minus C1. Okay, so this will give us the constant time operation of merging two parts. So basically, this is the operation we can use now when creating a segment tree. We will just make a full binary tree over our sequence, and in each leaf we will have information about only one element. So for each leaf, so for leaves, So if leaf has element A, so we know that for this leaf the pair VC will be just V is equal to A and counter is equal to 1. And when we have like an inner node which merges two parts, we know the value of VC for each part, and then we can calculate the value VC for the parent node. And then when we have query about some part of the sequence, we just need to calculate the split of this segment to the base segments of the segment tree, and we just have to merge them using this operation. So every merge is in constant time, and we know that for each query we will need at most logarithm number of merges. So then each query will so for query we will take logarithmic time, and then we still need logarithmic time for actually verifying whether this candidate which we have here is real leader in the sequence. Okay, so this is one approach to this problem. The second approach is I think a little bit easier, but it's a randomized approach, so it's not bulletproof. Here we know that we definitely will get the right answer. So what is the randomized approach here? So in the sequence, we know that we are looking for the number which occurs at least half of the time. So we know that if there is a leader in the sequence, it is very frequent. So we can try something like this. Let's take a random number from this sequence. So if the sequence has a leader with probability 1/2, at least 1/2, this random number will be actually the leader. So we can take this random number and test using this prefix sum approach whether this is real leader or not. So of course, if the segment has no leader, then of course we won't find it. So we don't produce wrong answer then, but we can produce the wrong answer if the segment has a leader, like it has 5 here, but we end up choosing randomly the wrong number. So if we choose randomly 3, then we lost. Yes, because we will say that there's no leader and actually there is one. But the probability of error is at most 1/2. So how can we reduce this probability? Yes, basically we can test several times. So basically what we can do is let's say that we test k times. So we can calculate the probability when all of these tests fail. So the test fails with probability at most 1/2, and in order all of these tests to fail, we would have 1/2 over k. So basically the probability that at least one of these tests pass is 1 minus 1/2 over k. And we need to find a k which will give us a reasonable probability that we won't fail. And actually, if we take k equals to 10, then this probability will equal to something like 99.9%. So we are pretty much sure that this will be we will get the right answer after like testing 10 candidates. Okay, but there is, but this is the probability of finding the solution to one query. And the problem is that in the test, we have multiple queries up to like 500,000, and we would have to give the correct answer for all of these 500,000 queries in order to pass the test. So actually, this needs to be multiplied a little more, because we need to multiply the probability of finding all of the queries. And okay, so this is the probability of succeeding in one query, and actually we need to calculate the probability of succeeding in m queries. So we would have to calculate this number, like probability of success in one query up to the power m, because we have here for m queries. And it turns out that even if m is big, like 500,000, the k is actually not so big. So as I have in my notes, k like 26 should be enough to give the same reasonable probability of error even for very big numbers of m. And of course, like the precise number of k can be tested like by submitting solution, because the higher the k you have, the more like probability of getting error is less. But of course you are like you have the danger of hitting time limit for bigger numbers of k. Then this could be like done with binary searching over the with submissions. But still, this like this k is in the bounds of the logarithm, which we have in this in this problem with segment tree. Then it should be okay. Actually, for this one, you have to be a little bit more careful, because here you have here you test 26 candidates for each query, but you still need to, if you do it like one query by one, you still need to multiply it with the logarithm n, which comes from the part of testing whether this candidate is actually good or not. And this could be a little too much. So the idea is you can have another idea. Basically, you can first find the candidates for all of the queries, and then test all of these candidates at the same time. So you can, so instead of having this array here, you can first, for every query, find the candidate, and then sort all the beginnings and the ends of the query. So if you have this sorted, you can start once again creating this array by going through the whole sequence, and every time you are in some position, you know what are the numbers of occurrences of all the numbers before that position, and then you can answer calculate the answers to the ending positions of the segments from the queries, which end here. Separately, you can do this for the beginnings of the query, and then for each query you have like the prefix, this prefix and this prefix, and you just make the you just subtract them. So basically, for this solution, you will still get n log n, because you have to sort all of the queries. So it will be like m log m to sort the queries. But for this solution, you need only to sort the queries once. And you can do something something like that. For each query, you find the first candidate, and then you do the whole pass through the sequence. Then for each query, you can try the second candidate, and once again you got the whole pass, and up to, so you will have like k passes through the whole sequence. And you only sort the ranges once, so the total complexity will be m log m from sorting the ranges, and then you have k times n plus m for answering the queries, because you have k passes over the sequence, and you have n plus m time for one pass. And this will be should be accepted. Okay, so that's it. Any questions? Okay. If not, I have a small announcement. So as you can see, but I will repeat this. The Absolving is for all of the days is open, and I think it will be open like for at least several months after the camp. This is one thing. The second thing is I put a public announcement in the system that I prepared some notes with hints for some of the harder problems from the previous days. So for instance, for day 1, there's a hint for transmitters, for polarization, and for the polygon. For day 2, I presented a pretty much like the whole write-up for the problem Scout, because many of you asked for this. And also for day 2, there's a link for the official Polish descriptions of the solutions. So if you would like to use like Google Translate or just look at the numbers or time complexities, you can also find some hints there. For day 3, we already talked about couriers, and there's this task about meteors. And there's a pretty much nice blog post on Codeforces for dealing with this task. It is a nice application of binary search, which is parallel binary search. And I think this blog post is enough for you to get the right idea. So actually, we won't be covering this this task here. So yeah, so basically you have these hints. Maybe I will also prepare some hints for other problems we didn't talk at the lecture sessions, but yeah, so that's it. And on the previous 2 days we started with I talk about the tasks from the easiest to the harder ones, and then I talk until we hit the time limit of the lecture. But today, apart from the easy part, the easy task of couriers, I will do another approach. So now I will talk about the hardest task. So actually, we will start with the tasks which get no accepts at all. So at least from the last contest, we have at least 4 tasks which get no accepts. So we will try to cover these tasks today. So today will be a little bit different. Okay, and during the contest we had 2 tasks which involve some kind of games. We had the task Nim with a twist and the task game from the last contest. So I think it will be it will be useful to cover some basics of the Nim game. I think most of you should at least heard about Nim, because it is like the main fundament in the combinatorial game theory. So basically, this game is between two players. Usually, we consider games between two players which make alternative moves. And in this game, we have some stacks. And on these stacks, we have some, let's say, coins, tokens, or whatever. Okay, and basically this, like the order of the stacks doesn't matter, and the only thing which matters is how many coins we have in each stack. And the move consists of choosing exactly one stack and taking some positive number of coins from this stack. So perhaps, the valid move would be like taking maybe the second stack and removing like maybe the 3 coins from the stack, or maybe remove all of the coins from the stack. At least 1 coin must be removed. And if the player cannot make any move, so it basically means that all of these stacks are empty, then this player will lose the game. And usually the question is, who has the winning strategy in this game? So if we know that both players play optimally, so they both want to win, knowing that the second player also play optimally, so who will win no matter what the other player, how other player wins. So basically for Nim, there's no theorem which allows us to calculate who has the winning strategy in the game, based only on using only simple arithmetic operations on the heights of the stacks. So basically, if we have this kind of games, it's useful to see what is really happening in the game. So for instance, what type of moves the player have and how it changes the state of the game. So here, when we have Nim, the state of the game is just is represented by the sizes of the stack. So we can make some kind of a graph, in which the vertices will be the states of the game, and we will have edges and every edge in the graph will represent a valid move. So, for instance, we can say that if we have like 2 stacks, so maybe the first stack has size 2, the second stack has size 1, and this is a valid state in the game. So what kind of moves we have here? So one valid move would be like to remove 1 token from the first stack, and we end up in this in the state in which we have 1 and 1 token, but we still have additional moves. We can like remove. We can remove both of the tokens from the second state, and we can remove a token from the only token from the second stack. Okay, and from these states we will also calculate the all possible moves. So for instance, for this state, we know that we can remove the first element, so we end up in this state, or we can remove the second one. So we end up with new state 1, 0. So for this guy, we have only one possible move, which is 0, 0. For this guy, we have two possible moves. Either we remove one element and we will go here, or we remove both of the tokens and we will end up here. And also for this one, we have only one possible move, which ends up here. And this is the ending position in the game. This is the losing position because we don't have any possible move starting from here. Okay, and this graph is like representing the whole possible state, like all the possible states we can achieve starting from this initial state in the game. And now we can label each of the states with the label which says either the state is a winning position from the player which starts from this state, or this position is a losing position. So, for instance, if we end up in the state where there's no tokens on the stacks, we cannot do any move. So we are so this will be the losing position for us. We cannot do any move. Okay, so what about this guy? So here, if we are here, every possible move, actually there's only one move, so this move goes to the losing position. So basically, if we are the player who starts at this position, we had a move which goes to the losing position, and the second position will be the position in which our opponent starts. So this is the position for our opponent, and this is losing for the opponent. So we know that for us it will be this position will be a winning position. So this one is winning for the first player. Okay, so essentially the same is here. In this state we have two moves, one for the losing position and the one for the winning state. But we are the player who controls which move will be made. So as long as there is at least one edge to some losing position, we know that this position is winning. So once again, here we have winning position because we have only one move to the losing position. But in this state, the situation is different. In this state, every possible move, we have two moves, it goes to the winning position for the second player, for the opponent. So no matter which move we choose, we know that opponent will end up in winning position, so this position is losing for us. And the position at the very top, is it losing or winning? It's winning because it has at least one move to the losing position. Okay, so that means that with this algorithm we can calculate the losing and winning positions for every whether the state or position is winning or losing. And if we are asked to say who has the winning strategy, for instance in this top state, if it's winning, the first player has winning strategy. If it's losing, the second player has winning strategy. Okay, so so we can do this for different kind of graphs, not only for the game of Nim, but also for other games. For instance, in the task from the last contest, we had a different game. We had a game with some pawns on the board, and you had some rules about how these pawns can be moved, and you can construct the very similar the very similar graph of the game, and of course, in order to this algorithm to work, this graph should be acyclic. So basically, if you have some cycle in this graph, then there's a possibility that the game will end up like forever, because the players, the game will never end. So we will considering here the game which does cycle in the graph, and for instance, here you can see that there's no cycle because from every an edge from some state to another state. Is it like this clicking noise? Is it okay? Okay. So if you have this the edge from some state to another state, you know that the total number of tokens on the stacks is decreasing. So like for every edge, the total number of tokens is decreasing. So you know that you can sort this graph topologically. For instance, by the numbers or by the total number of tokens in the on the stacks. So this graph has no cycles, and then you can pretty much do this algorithm using dynamic programming from the bottom to the up. So you are starting with the like you are calculating this losing winning labels for based on the topological sorting of this graph. Okay, so this algorithm will work. Actually, one this algorithm. Yeah, I think something is wrong. Okay. So we want. Yeah, it's okay, because it looks like it didn't. Yeah, it didn't help. Should I continue? Okay, okay. So, yeah, and there's no this clicking noise anymore. So I think we're good. Okay, so basically, what we can do here, we can just like merge these states So we can like merge every possible state which only differs in the ordering of the stacks. But still, it won't save us from the exponential blow up of the numbers of the states. But this is like a good image which shows us what to do with the new kind of games. And sometimes, actually, sometimes you have the games in which the state, the number of different state is reasonable, and then you can just use this algorithm to calculate the winning or the probabilities without like getting into the details of the mechanics of the particular game. So if the number of different states is bounded, like 1 by 1 million, then you don't have like to analyze the game. You just run this algorithm. Okay, so what if the number of states is very big? Then you have to like look at closely what is happening in the game to actually came up with the better algorithm for calculating the winning or losing strategy. And actually for the Nim there's this nice algorithm. So you can like try to in order to find out what is the algorithm, you can like see what is happening for the smaller games. So for instance, what happens if you have only one stack? So if you have only one stack, so for instance it has like 4 elements, then you know that if you're the first player, you can like remove everything. You can remove everything, and then the second player will have no possible move. So if the number of stacks is 1, so let's say that the stacks are like A1, A2, up to AN. So this is like the number of elements in the stack. So you know that if A1 is non-zero, you can make a valid move by taking A1 elements, and you know that this is the winning position. And of course, if A1 is equal to 0, this is the losing position, but because you cannot do any move. Okay, so the second easy case is when n equals to 2, and actually then you have 2 different cases. One case is when A1 is equal to A2. So for instance, you have like maybe you have like 4 elements and 4 elements. So you can see here that if the first player makes any move, for instance, like remove two tokens or 2 coins from the first stack, you can see that the second player can repeat the same move on the second stack. So it's like stealing the strategy. So he can like repeat every move which the first player do on the first stack. So he can take 2 guys here. So any move the first player do here, the second player can repeat. So and of course, if the first player makes a move in the second stack, the second player will repeat it on the first stack. And you see that finally the first player will have to take the last coin on some of the stack, and then the second player can repeat this move, and the second player will be the player who takes the last coin, and the first player will lose. So in this case, the second player has the strategy which gives us the winning no matter what will happen. So we know that when AI is equal to A2, this is the losing position for the first player. And okay, so this is well these 2 guys are the same, and when these guys are different, so for instance we have maybe 6 and 4, So what will happen here? So here, the first player can move to the position in which both of the stacks are the same height. So he can take 2 items from the biggest stack, and then both stacks are the same size. So we know from the previous example that it's the losing position for the opponent. So this is the winning position for the first player. So these are the small cases. You can try to think about what will happen when we have 3 elements. But this gives us a pretty good intuition what's important in this kind of games. One thing you can you can use in this game is this argument of stealing strategy or some kind of symmetry in the game. So for instance, you can if you have more stacks, and if you see that 2 stacks are the same size of them, so we can see that this will apply to them. So basically, if you have so let's say that we have 3, 5, 3, 2, 1, and I won't be drawing more coins here, but basically you can see that you have 2 stacks which are of the same size. So basically, if you if one player takes makes some move in one of the stacks, the second player can also copy this move on the second stack of the same size. So actually, it turns out that this a similar strategy will end up when we have a similar game in which we don't have these 2 stacks. So if we have 5 to 1, the similar strategy will be the same as in this game. So it will be it could be a little more involved than this case to see that why it's happening. But basically, this gives a little bit intuition why the general algorithm for the Nim works. And the general algorithm is as follows: we take the XOR of all possible heights and of the heights of the stacks, and we see what is the value of this XOR. And based on that, we know who has the winning strategy. So let's say that we denote the XOR operation by this plus in a circle. So this is XOR. So we just take we take 2 numbers and we add them up, but without carry. So this is like adding each bit of the numbers modulo 2. So basically, we are calculating this number, and if this number is equal to 0, then we have the first player has losing strategy. If this number is not equal to 0, then he has a winning strategy. So so basically, we can see what is happening if this is true for our simple examples. So for instance, if n is equal to 1, the XOR of one number is just this one number. So we see if this number is positive, so the XOR is all so the XOR is also positive, so we have winning strategy. If number is 0, then we have losing strategy, and this guy also said we have losing strategy. And with n equals to 2, the XOR has this nice property that if we take two numbers, the same numbers, and we XOR them, we will get 0, because XOR basically is like we are writing these numbers in binary, and the x is, and we will just like summing each of the columns independently. So 2 zeros get us 0, and 2 ones get us also 0. And if you have 1 0, then we will get 1. So we will see here that we will get 0. So basically, if we have two stacks of the same size, we will get 0. So this is a losing position, and we have here. If we have two numbers which are different, so if we have like x and y, and x is different to y, then we know that they need to differ in at least one place. So if they differ like here in this bit, so we know that this number cannot be equal to 0. So we know that if we XOR two different numbers and they're different, there we have its XOR is a positive value. Okay. So basically, how can you prove that this calculation holds? So you can prove this by actually showing three cases which are presented in this graph. So we have three cases. The one case is we need to show that for every ending position, so in which the position which we don't have any valid moves, we have the losing. This is the losing position. So when we don't have any move, we know that all of the stacks must be empty. So the XOR of all of these stacks is equal to 0, because we only take XOR of the numbers which are 0. So this is 0. This is the losing position, and of course the ending position is the losing position. The second part is what will happen if we have a winning position. So if we have some winning position, so we know the winning position is the position in which we have at least one move to the losing position. So basically it boils down to what's happen if we have a XOR which is positive. If we have XOR which is positive, we need to show that we have a move to a situation in which XOR is 0. So this is a losing position. So, but basically, if the XOR is not equal to 0, so we know that we have some numbers, and we can like write down these numbers as in binary, and now we can make a XOR out of them. So this will be something like that, and this XOR is positive. So we can look at the highest bit, which is 1 in this XOR. So because this okay, so because this bit is because bit is high, is 1, so we know that there's at least, so then we know that in this column there's an odd number of 1s, because if it were like even number of 1s, we know that this will be 0, this would be 0, so we have odd number of 1s here, so we know that we have at least 1 1. So here this is the only one here. So what can we do here? Because we need to show a move which will be which will get all of this to 0. So this move will be, we will take some coins from this stack A2. So the move will be as follows. We'd like to remove this one. So we would like to put here 0. So we will get 0 here. And then we would change these bits in such a way that to 0 all of these bits here. And this change, and actually because we are changing the highest bit from, okay, we are changing this bit from, the highest bit we are changing from 1 to 0. So actually we are decreasing this number. Here we can change some bits from 0 to 1, but they are like after this bit, so it doesn't matter. What I'm saying is just this is the decrease of this number. So actually, this represents some valid move in the game. We are just taking some specific number of coins from this stack, and this will give us the move which goes to the XOR, which is 0. So it goes to the losing position for the opponent. So we know that, yeah. So basically, this is the if the XOR is positive, we can say that this is the winning position. And we have the third case. The third case is to consider losing positions. So we must show that if we have losing position, namely if we have XOR equals to 0, every possible move goes to the position with XOR equal, which is non-zero. So again, this can be shown using this bits, because if we have some XOR which is 0, so maybe this is something like this. Okay, so here we have all zeros. So basically this means that in every column we have even number of ones. But if we take like any stack and we reduce number of coins in the stack, we know that at least one bit in this number must change from 0 to 1 or from 1 to 0. And so for instance, so here, yeah, so to reduce this, here this bit must change from 1 to 0, and these guys, at least one of these guys must change from 0 to 1. But basically, there's at least one column in which we have a change, so the number of ones change from the even to odd. So we know that we will have at least one bit set in this value. So we know that this value is not equal to 0. So if you have XOR 0 XOR, then every possible move goes to the non-zero XOR. So basically that means that this boils down to this: we have losing position, and every losing position goes to the winning position. So basically this means that this value of XOR is the correct way to identify losing and winning positions, but because this information is consistent with the definition of what is losing position and what is winning position. Okay, so we don't have to like considering all of the graph. If we want to see what is the winning position in Nim, we just take all of these heights of the stacks and we calculate the XOR of them, and we can do this in linear time. And if XOR is positive, this is the winning position. If it's negative, this is the losing position. Okay, so this is Nim, and our games from our tasks were a little bit different. So let's start with the game from the from the last contest. So the game in which we have some coins on the in the row. Okay. So in this game we had some coins in the row, and we can like move the coins from left to right. So at the first sight, you could say that that this game has like nothing in common with Nim, but actually this is Nim in disguise. So this is the game in which knowing the strategy of the Nim will be very fruitful to us. And actually there are actually many games in combinatorial game theory which looks like they have like very different mechanics than Nim. And it turns out that if you look at them in some different perspective, it will turn out that they have like actually the very similar strategy as in the Nim game. So maybe before going to our task, we'll look at one more classic game, which is very similar to Nim, but at the first sight it looks pretty much different. So the game is called Staircase Nim, and in this game we still have some stacks, but now the stacks are numbered from the order of the stacks will be important. So let's say that these are like number of the stacks, and here we will have like how many coins we have on which stack. So let's say that here we have like 3 coins, we have 2, 1, 2. And a possible move in this game is taking, we choose one stack, we choose how many coins, some positive number of coins we would like to remove from the stack, but in Nim we just we throw away these coins. Here we have to put these coins in the stack which has the smaller number. So for instance, the valid move will be like taking maybe taking 2 coins from the stack number 6 and putting them in stack number 5, or maybe taking two coins from stack number 2 and putting it on stack from stack number 4 and putting on stack number 3. If we have some coins on the stack number 0, we cannot move them. So basically, the ending position in this game is when all of the coins are moved to the stack number 0. Then we cannot move them anymore. Okay, so this game has some similarity with Nim, but actually we don't like remove the coins at all. We're just moving them. So one thing to note here is the thing to observe here is that we also have this. This game is also finite. So it cannot be that we will like end up in the loop, because in a Nim we know that the total number of coins is decreasing in every move. Here we have the total number of coins stays the same, but if we calculate the total distance for every coin to the stack number 0, we see that this total distance is decreasing in every move, because we are moving at least one coins, and we're moving it from right to the left, and finally all the coins will be moved to stack number 0. So in this case, also this game is finite, and of course it will be fruitful to us to look at the very easy examples for this game. So let's say let's say that we have 2 stacks. Of course, if you have like 1 stack, it's all of the coins are in 0, so it's not very interesting. So we have 2 stacks. So basically, it doesn't really matter that if we have some coins on the 0 stack or not. So let's say that we have 0 here, and we have some A1 coins here on the first stack. So what will be the winning move here? We move every coin to the 0 stack. So basically that means that if A1 is non-zero, then we have like a winning move. And if A1 is 0, we are in the losing position, because there's no coin to move at all. So, well, at least for n, for very small n, so at least if we have 1 stack which is interesting, so we have the same we have the same strategy as with Nim. So maybe it has something in common. So let's say what is happening if n is equal to 3. So let's say that we have some A2, A1, and here we have 0. Okay, so let's calculate the same idea. So maybe A2 is equal to A1. What it will give us? So here the valid moves are we can take some coins from A1 and put it in here on, or we can take some coins from A2 and put it here. So actually, the second player cannot like copy the moves of the first player, because we don't have this symmetry between these 2 guys. Okay, so what is actually happening here? So maybe so actually maybe let's consider a little bit simpler example here. So let's say that, okay, we have 2 stacks, but the stack A1 is empty. So what will happen now? Okay, it looks like the first player will lose, and now we can apply the same strategy of like copying move by the second player, because if the first player takes any number of coins from the stack A2 and it move it to the A1, the second player can make the same move but from A1 to the last stack. So you can copy the move, but on the second stack. So every time the first player moves some number of coins, the second player can copy it. So actually, here we see that the first player will have a losing strategy. And actually, that means that we know what is happening if A1 is non-zero. So what can the first player do here if A1 is not 0? yeah, he can take every coin on A1 and move it to 0, and then it reduces the situation to the situation in which A1 is equal to 0, and this is the losing situation. So, and because this losing situation will be for the opponent, so the first player with this move guarantees the winning strategy. So actually, when we have two stacks, we have a little bit different winning strategy than in Nim, but it's interesting that this strategy, I mean, this losing winning, the difference between losing winning does not depend at all on the size of the stack number 2. It doesn't matter how many coins we have on stack number 2. It only depends on how many coins we have on stack number 1. And it turns out that this could be generalized a little more, and it turns out that the general strategy for this game because this kind of moves, sync moves, will also hold for all of the stacks which are on even positions. So, for instance, if the player makes some kind of move from the 4th stack to the 3rd one, the next player can copy it to the second stack, and still they will be like on the even stack. So, if we have some coins on the even stack, actually the number of coins of the even stack does not matter. It will be like the same argument as here. So actually, even stacks are like they, as well as the luck stack. Well, it's a 0 stack. It doesn't matter how many coins do we have here. So it turns out that only odd stacks are interesting, and we can see something interesting here. So if we have some coins on the odd stacks, so every move which uses the coins, moves the coins from the odd stack, it moves them to the even stack. Okay? And actually, the number of coins of the even stack does not matter. So basically, we can see that this is essentially removing these coins from the game. Okay? So if it's removing the coins from the game, so basically it looks like some kind of Nim. And basically that's it. We have to calculate the XOR of every odd stack, and if this XOR is equal to 0, then we have losing position. If this XOR is non-equal to 0, we have a winning position. And it's like consistent with the small examples we have here. Of course, this is not a rigorous proof we have here, because there's only we have also moves which goes from these even stacks to the odd stacks. So actually this is not the same as Nim, because here we have moves which introduces us new coins on the stacks. So actually this looks like Nim, but we have additional moves in Nim in which not only we can remove coins from stacks, but we can also put some additional coins on the stack. But observe that we can add these moves to Nim, and it doesn't really change the strategy of the players, because suppose the first player has a winning strategy, so it has a winning strategy with the original moves of Nim. So the first player doesn't need to do any additional moves of introducing new coins on the stacks. So for the player which has a winning strategy, the new moves doesn't matter. They don't matter. And if a player has the losing strategy, so the XOR will be 0. So this player can say, okay, so I have losing strategy with the old moves of removing, so maybe with the new moves of introducing new coins on the stacks, maybe I can find a way to get a winning strategy. But the answer is no, because if the player with the losing strategy adds some more coins to the stack, the second player, he just removed these coins, and it will return to the original state. So in case of Nim, when we add this kind of moves, we will end up, if someone has a losing strategy, we'll end up like in an infinite game, because the player with the losing strategy will just add coins, and then the second player will remove them, and it will like goes forever. But in this game here, in star case Nim, we know that this situation of going forever is not going to happen, because like the number of these moves which introduces new coins to the stack is limited, because we know that every time the player adds some coins to the stack, the total distance of all the coins from the 0 is decreasing. So finally, after some steps, we will end up, the game will finish. So actually, this is precisely Nim for the stacks which are for the stacks on the odd indices. So the game looks kind of different, but it turns out that if we look at this game in a different perspective, it ends up being Nim. Okay, so finally we are ready to our game from the task. So in this game we had some board, we had some let's say, maybe it will look like that. I will make sure that this example is so maybe let's write something like this. Okay. So we have a board, we have some coins on the board, and every possible move in this game is to take some coin and move it to the first empty position to the right. So basically here, for instance, we can take this coin and move it to this position. So this will result in this image. Or for instance, we can take this coin and we cannot move it to the next position because it is taken by another coin, so we can move it to this position. And we will end here with this situation. Okay, and we have a valid move for every coin. What is the end position? The end position is when we have some coin in the last in the last cell of the array. So for instance, from this position there's a winning move of taking this coin and moving it here, and this will end up the game. So basically from this position the first player has a winning strategy, just moves this coin. And in the task we were asked to calculate who has the winning strategy, and if the first player has winning strategy, also to calculate what is the number of what is the number of winning moves. One interesting thing to notice about the Nim is, like, if we want to calculate what is the number of winning moves in Nim, it's always an odd number, because if we see here, like the calculating the winning move, we were finding the highest one, which is set here, and it turns out that the number of ones in this column is odd, so we have odd number of candidates of this stacks to. We have odd number of stacks in which we can remove some coins to get the winning move. So this is like a side note. Okay, so what happens here? So it turns out that we can look at this game in another perspective, and what we will do, we will look at the we will group the coins in some groups in such a way that that every group of coins will be separated by the empty field. So, for instance, okay, I will remove the blue arrows for a while. So, in this example, we have one group here, because this is the like the group of coins which are the cells in which the coins are close to each other, are next to each other, and this is the second group. But we will say that each group is separated by exactly one empty field. So here we have two empty fields. So this is also a group which is of size 0. So if we have like more than empty fields next to each other, we have some empty groups here. And here we have some group, and here also we have some group. So basically, we will let's number these groups from right to left. So here we have group 0, 1, 2, 3, 4, and let's look at the moves we can make. Okay, so we said that we can take this this coin and move it here. What will happen to our groups after this move? Okay, so let's see what is happening after this move. So after this move, we'll see something like this, and this is group number 3, because we are just removing this coin from this group. So this group is getting smaller, but actually, if you see here, we move this empty place here. So actually, this coin was introduced to the second group. So this is the second group. Okay. So basically, this move was it was moving the pawn from the third group to the second group. Okay. So let's see what is happening with this move. So with this move, we have something like this. We would take so here's the empty field also. So we would jump over this this guy here, and it turns out that the result of situation will be like this. We have still group 3, and now the group 3 is empty, and we have 2 pawns in the second group. And actually, if you look at all of the possible moves, if you look at how the groups are changed in during during the move, it actually you are taking some number of pawns or some number of pawns from one group and moving them to the group with the smaller index. Okay? So if you look at this game in terms of groups, what can you see? It looks like staircase Nim. Yes? If you look at this game based only what is happening to the number of pawns in each group. Every move takes some pawns from a group and moves these pawns to the group with the smaller index. So these are precisely the moves which we have in the staircase Nim. So it looks like this game is very similar to staircase Nim. And so one thing is to so as for the move, what kind of moves we have in this game, this is essentially the same as staircase Nim, but we need to be a little bit careful here, because one thing to check is we have to also check what is the ending condition for the game. So when does game ends? So basically, in the staircase Nim, we have this condition that the game ends when every coin is in the stack number 0. So if we had the same here, that means every pawn in the group number 0, that means that like every pawn has to be as close to the end as possible. So basically the ending position here would be like every pawn is at the group 0, so we do not have like any further move. But our game ends a little bit differently, because it ends as soon as at least one pawn gets to the group number 0. Yes, if we make this move here, it will appear that one point is at group number 0, and then the game ends. And this is not the case in staircase Nim. So here we have something a little bit different. Okay, but we can treat it as some kind of a special case, because let's see. So let's see what we have here. We know that the group number 0 will be empty, because otherwise it's like the losing position. We don't have any moves. So let's see what is happening with the group number 1. So if the group number 1, if it's not empty, if we have some pawns in group number 1, then we know that this is the winning position, because the first player can take any pawn from the group number 1 and move it to the group number 0, and it will finish the game. Okay, so if so we know that group 0, so number of groups in 0 is empty, and if group 1 is non-empty, then this is the winning position, and the number of winning moves is exactly the number of pawns in the first group. Okay, so let's solve the case when we have 0 elements in the group 0, and we have 0 elements in group number 1. Okay, so then we see that, so in group 0 and in group 1 we have no coins, but we have some coins in other groups. So then we can see that any move which goes from group number 2 to group number 1 will end up in losing game for us. Because if we make such a move to introduce some pawns to the group number 1, then we know that the opponent can take this pawn from group number 1, move it to group number 0, and the opponent will win the game. so we will lose the game. So actually, there's no profit in moving the pawns from group number 2 to group number 1. So basically, we don't want to do any such move. So the question is, when we are forced to do such move? Okay, because sometimes we will be forced, like the game must end. So when we will be forced to move from group number 2 to group number 1? Yes. So we will be forced to do this move when we end up in position in every pawn is in group 2. So if every pawn is in group 2, we must make a move to group 1, and we know the opponent will move to group 0, and the opponent will win. So we know that if we are in position when every pawn is in group 2, this is a losing position. Okay? And actually, now it looks like exactly as staircase Nim. Because if we, so this is a special case which can be handled separately, and otherwise we have this case, so group number 0 and group number 1 is empty, and now we can just forget about these groups and we can treat the rest of the game exactly as staircase Nim. So in order to see whether we have a winning strategy or losing strategy here, we just need to calculate the XOR of every group with the odd index. So basically, ignoring group 1, we need to calculate the XOR of groups like let's say G is the number of elements in a group, so G3 plus G5 plus G7 and so on. And if it's 0, we have losing strategy, so we don't have any winning move. And if it's non-zero, then we have some winning moves. And actually calculating them, like showing how to calculate the winning move is not very hard, because if this XOR is non-zero, so after our move we must make this XOR to be 0. So essentially what we have here, we have to consider moves from every group, and it turns out that for every if we say that we want to make a move from group number k to group number k minus 1, there's exactly one number of pawns we can move in order to this XOR to be this new XOR be 0, and it's easy to calculate it using the properties of XOR. So actually we have to consider every group, and we have to see whether there's a number of coins from this group to the another, which results us in the XOR equal to 0. Of course, we need to take care of because sometimes it can from the calculations it would be that we need to move more coins from the group as in order to XOR to be 0 as there are coins in the group. So this is not a valid move. So again, this algorithm will run in time linear on the number of pawns. So essentially, what we do here, when we are like reading the input, we are constructing the sizes of the groups. We're making the XOR, and then we have once again we'd go through the groups in order to calculate the winning moves. Okay, so this is staircase Nim. Staircase Nim and our game. So as I said before, we had one more game about Nim. It was a task Nim with a twist from the first day, and it has Nim in the title of the task, so it's not very strange that we will need some information about from here. And but actually, in this problem we were. This problem was more about dynamic programming than actually about the strategies in the game. So actually, in the problem we had some stacks, so basically the game will looks like normal Nim, but at the start of the game, one of the players can the first player can remove some stacks from the game, and then the game proceeds from the second player. So basically, we know the rules of the game. So we know that if we are the first player to move, and the first special move is to remove some stacks from the game, and then the second player starts the game. So we know that we need to remove the stacks in such a way that the XOR of the stacks which remain in the game is 0. So basically, we have to choose some stacks to remove in order the XOR to be 0. So essentially, if it was the question in the problem was, okay, can we remove some stacks in order to get to the 0? It will be pretty easy. So the task is a little bit harder. First of all, we are asked how many possibilities there are to remove some stacks, and also we need to remove the number of stacks must be divisible by d. So okay. So and also we need one more thing. We have one more constraint. The number of the stacks which are left cannot be 0. So we cannot remove everything, because then it will be pretty obvious that the second player has the losing strategy, and we don't want to be we don't want to do this. So basically, this boils down to this: remove some stacks, some number of stacks, remove some, let's say, remove some k stacks where k is divisible by d. And from the constraints, d was not very big, it was like 10. Don't remove everything. Okay, and XOR of remaining stacks must be 0. And we are asked how many possibilities we have to make such a removal. Okay, so we will be doing dynamic programming here, and so maybe let's look at the constraints of the problem, because they will be quite important here. So from the constraints we have n is up to 500,000. So n is 500,000. AIs are also up to million. And one additional constraint is that the sum of AIs is equal to m is smaller than 10 to the 7th. Okay, so so basically in our dynamic programming, we will have the three-dimensional array. So so as a standard thing here, we will like in the knapsack, we were considering items one by one. So we can consider here the stacks one by one. So we will be like having. So let's say that we consider stacks from 1 to I, and this means that we chose some of these stacks to be removed, and in DP we will calculate how many ways we can do this. But we still need to like maintain a little bit more information about these stacks because we need to control what is the that the number of stacks which we removed is divisible by d. So basically it boils down to controlling what is the remainder of the number of stacks we already removed. So let's say that this will be the remainder of the stacks of the number of stacks we removed, and this r will be like from 0 to d minus 1. Okay, so this is one thing we have to control. The second thing, so this is this thing. The second thing we have to control the XOR of the remaining stacks. So we also need to like consider all of the possibilities for the XOR. So let's say that this will be the last element in our array. So this will be the XOR of the remaining stacks. And we will see how this number is big in a second. And we still have one additional requirement, that we don't remove everything. And how can we handle it? Basically, it's not very important, because it will happen only in one case. So when we would like to remove everything, so we would like to remove everything. And if actually, because number of stacks removed must be divisible by d, this is only case when n is divisible by d. So this is only important if n is divisible by d. Okay, but if it's the case, n is divisible by d, so if we want, so then we would like to remove all of these stacks. This is one possibility, because then we have no stacks at all, and the XOR of the stacks is 0. So this is one good possibility to do this. But okay, so we know that we can do this. So let's forget about it. Like let's forget at all about this requirement, and if we know that n is divisible by d, then we need to decrease our answer by 1, because we will calculate this possibility that we remove everything, so we decrease our answer. So actually we don't need to worry about this requirement anymore. So we are only left with this, these two requirements, and this will be handled by our dynamic programming. Okay, and the recurrence formula for the dynamic programming is pretty easy, because so basically it means, okay, we will consider now the stack number I. So we have two cases. Either we remove the stack or we don't remove the stack. Okay, so let's say that we don't remove this. So in this case, if we don't remove the stack number I, so for the previous stacks from 1 to I minus 1, we still have the same number of stacks removed. So the remainder of the number of the stacks removed is the same. So we put R here. Okay, but we didn't remove stack number I. So the XOR of stacks which remains will be different. So we know that with stack number I, so let's say that S is the number is the XOR of the stacks from 1 to I minus 1, and then we are adding stack number I, which we don't remove. And this number must be equal to X, because this is the XOR of all the stacks from not removed stacks from 1 to I. But thanks to the properties of the XOR, we can XOR all of the sides of the equation with AI. So we can like XOR it from both sides, but let's write it like here. So this is equal to X, but if we can XOR both of the sides by AI, and actually from this property, and we can see that here we have 0. So actually S is equal to X XOR AI. And S was the size of the remaining stacks for stacks from I to from 1 to I minus 1. So actually here we have S. So basically here we have X XOR AI. And this is one case of our dynamic programming. This is the case where we keep stack I. Okay? So we still need to consider the second case in which we remove the stack number I, and we just need to add the number of possibilities for when we keep stack I and the number of possibilities when we remove it. So this will be once again dp from I minus 1, and now we are removing stack number I, so the remainder of the number of stacks which we keep is different. Here we need to decrease this number, so here we just put R minus 1 modulo D. Okay, but on the other hand, on the last coordinate we have just X, because we removed stack number I, so the XOR from the remaining stacks is the same. So this is the case when we remove stack I. And of course this will be taking modulo M, because we are calculating the answer modulo some big number. Okay, so this is the recurrence formula. It's also quite easy to see what will happen for the basic case. I mean, if you have, we can initialize this with 0. When we have 0 stack, and we have, so in which case when we have 0 stacks, we know that XOR is 0, and also the remainder of the taken stack is 0. So In this case, we have like one trivial possibility, and for all other cases with 0, so for all other cases we have 0. So these are boundary cases for here, and okay, so we need to see what is the time complexity here. Again, like the calculation of one cell of the array is in constant time, so the time complexity only depends on how many cells we need to fill. We already know that in the second coordinate we have d possibilities, and d is quite small. On the first cell we have like possibilities from 0 to n, and what we have in the last cell. So in the last cell we have to consider all possible XORs which can be resulted from our numbers. So let's say that big A is maximum from A1 to AN. So if A is a maximum, so we know that A is some number which has some bits. So let's say that okay, so let's say that 2 to the power of k is the smaller power of 2, which is greater than A. Then we know that if we have some numbers, then we know that number A fits into k bits. So if every number we would like to XOR fits into k bits, then we know that XOR also fits into k bits. Okay, so this number here will be from 0 to 2 to the power of k minus 1, and this number can also be bounded from the upper side by 2 times A. So we can just say that like this third coordinate is approximately bounded by the maximal value of the element. Okay, so what is the time complexity then, and what is the memory complexity of this algorithm? Like we have n, because this is the first coordinate. We have multiplied by d. This is the second coordinate, and multiplied by a. This is the third coordinate. So, in terms of time complexity, this is pretty much too much. Because n is up to million, and also a will be up to million. So this is something which will be too much for us. Okay, so how to speed it up? So actually, before we go into speeding this up, let's see that if we can have this time complexity, but also this is the memory requirements of our solution, because we have this big array. But let's say maybe we can remove some memory first, and then we go to the time complexity of a solution. Because also in this task we are not only bounded by the time, but we are also bounded by the memory, because the memory constraints were about 64 megabytes. So it was really small amount of memory we have. So let's see what we can do with memory in this task. And in terms of memory, we can do the standard thing. So let's see at this at this recurrence, we see that the element I only depends on the cells with the value I minus 1 here and here. So we can do the standard trick. We don't have to store the full array. We only had to store two values for I. So basically, if it's like the quadratic array, we say that we store only 2 rows. Now our array has like 3 dimension, but the idea is essentially the same. We store only 2 values for 2 different values for I. So our like memory will. So first, the first idea will be store 2 rows. So basically, what we are having here, we store dp 0 and all possible values, and we okay. So I will be from 0 to 1. But this is like the standard trick we can use, and thanks to that, the memory requirement is not n times d times a, it's just d times a. But we can do one more trick here, and actually we can store only 1 row, and this will needs us to look a little bit closer at what we are having here. So we see that value of I depends only on I minus 1 and I minus 1, but the second important thing is that value of x on the third coordinate only depends on value of x and of value of x plus ai. So let's see on which values depends value x plus ai. So if we have x plus ai here we would have x plus ai, and here we would have x plus ai, which is equal to x. So essentially, what we are having here, if we have 2 elements, x and x plus ai, they are like depending one on the other. So if we have these 2 guys, they are depending on the same 2 guys, but in the row I minus 1. Okay, so what can we do? We can have only 1 row, and we can do the calculations for the pairs x and x plus ai separately. So what we'll have here, we have only 1 row of dp. So we have only dp which depends on r and depends on x, and we will calculate this dp for the next row using the pairs, calculating it separately for pairs of x and x plus ai. So basically, what we do, we take this pair, and what we need to calculate, we need to calculate dp of value r. So let's say that we copy this. We will store the answer in another array. So let's say that this dp with a star, and this dp with the star has it has to be have room for all possible r's, and has to be room for 2 elements. So let's say that this is like x star, but x star is only needed to be equal to x or x plus ai. So basically, these are 2 elements. So we have 2 elements here and 10 elements here. So we can. So these are the elements which need to be calculated for the new row if we are only considering this pair. Okay. So we create the array of size O of D, which is, because D is like 10, we can see that like it will almost of constant size, and depending on the values of dp, we will calculate the values in this array using this recurrence formula. So in dp here, in array dp, we have the values for row I-1, and we will calculate the needed values in row number I, but we will store them in this additional array, in this very small array. Okay? And we will see that only these values are depends on these values. So after we fill this small array, we can then copy it to the original array, and that's it. And we can start doing the same calculations for the smaller for another pair. Okay, that will allow us to store the whole information only in one row. Okay, so this is a nice trick which is which really use the specificity of this problem, but it will allow us to store the whole information in one row. And at this point of the solution, it's maybe not very clear why we need this, because still we have troubles with the time complexity of the whole solution. But we will need it a little more later. Okay, so what is the problem with the time complexity? So value d is small, it's 10, so it doesn't really bothering us. But the problem is with this XOR. So this XOR could be really big, but fortunately we have still one constraint from the problem which we didn't use at all, and this is the number. This is the constraint of the total sum of the sizes of the stacks, and we didn't use it yet. So basically, if we have like the large number of stacks, but the size is limited, so we know that not every stack could be as big as 10 to the 6th. So if we have some big stacks in our Nim, then we know that because of this limitation of total size, a lot of the stacks will be actually small. So we can use this information, because if we are considering the stacks from 1 to I, the XOR which can be resulted from these stacks is actually not bounded of the maximal value of A of all of the stacks, but only on the maximal value of the stacks from 1 to I. So what we can do we can sort the stacks by their height, and we will be considering stacks from the smallest ones to the biggest ones. So every time we do this calculation on dp on row I, this will be not so. So actually, previously this was bounded by some power of 2, and this power of 2 was bounded by 2 times the maximal value. So now, so before it was bounded by 2 times max of all of the numbers, now it will be bounded by maximal for all of the numbers, but up to ith stack. So here we don't have n, we have I, but we know that this we sorted the stacks, so we know that this is actually bounded by 2 times AI. Okay, so this is like the maximum value. Of course, we here we will use the correct power of 2, but this power of 2 will be between AI and 2 times AI. So let's see what the time complexity we will now have. So here we will be treating every row separately in terms of calculating how many values we can store in every row. So here we have D, and in the first row we need to store up to 2 times A1, in the second row up to 2 times A2, and so on. So basically it will be the sum of these values. So basically this is D times the sum of them, and this sum is bounded by M. So this is D times M. Okay, so basically every next row of the dynamic programming will be bigger, but every row of the dynamic programming will be of size approximately the size of the stack, and the sum of the sizes of the stacks are limited. So actually the sum of the rows in our dynamic programming is also limited by n. And of course, like we treat this R separately, so we are multiplying it by D. Okay. So now the time complexity looks reasonable because we have 10 times 10 to the 7th, so it was like 10 to the 8th, so it should pass the time limit. But still, we would have problems with the memory here. So once again, we can make the standard approach of storing only 2 rows. So when we would store 2 rows, we would need okay. So we would need 2 rows of the memory. In each row, we have D up to 10. So we would have 10. Then we would have the power of 2. Which is so we would need the memory to store the longest row. So it would be like, okay, it will be like 10 to the 6th. Okay, something like that, or 10 to the 6th times 2. Okay, actually we need to no. Actually we need to the smallest power of 2, which is greater than 10 to the 6th. So actually we can say that this is exactly 1 megabyte of values. So this is 1 mega of values. So this is like 2 to the power of 20. And still we need to incorporate the size of one cell, and the size of one cell is 1 integer, so this is 4 bytes. Okay, so this would give us 80 megabytes of for storing. So this would give us 80 megabytes of storing 2 rows of memory. So it's a little bit too much if we have only 64 megabytes. But we had this one special trick that we actually can reduce it to one row of memory plus some constant memory for the smaller array. So here we would have like 40 megabytes when we apply this trick of storing one row. Okay, so that was it for this task. So apart from knowing like the Nim strategy for XOR, the strategy for Nim that involves XORing things, this task was not really about the game itself. It was more about like interesting things you can do to like speed up the dynamic programming or squeeze it into memory. But I think it is worth knowing because these ideas can be like also applied to other problems. Okay. So that was the two hard problems, one from day one from day 3. And I think we will have today we'll have time for one more problem, and we will talk about the problem variety from the last contest. Okay, so the problem variety. So the task statement of this problem was very easy. So basically we have the array of numbers, and we need to consider every possible sub-array of size k, every square of size k in this array. And what we are interested in this for every square, we would like to calculate the number of different values which appears in this square. So, for instance, if we have like square of size 2, and the square looks like this, then we have 3 different values. We have 1, we have 2, and we have 5. So for this square, the answer is 3. And in the task statement, we were asked about so for every possible, if we calculate it for every possible square, then we are interested about the total, the sum of these numbers and the maximum of these numbers. But it was only this was only for the answer to be small. But actually, in our algorithm, we will really calculate the number of different values for every possible square. So the solution will be a little bit more general than what is asked in the problem. So if the array is of size n times m, then we have like a very naive solution of taking every possible square and like calculating number of different numbers in the square by just adding numbers one by one. So we have like n times m candidates for the square, and this will results in the algorithm k squared, because for every possible square we will just naively calculate these numbers. And because these now like the numbers are in a range, let's see, for 1 to c or c as up to, let's say, million, we can just make an array for storing the counters for every possible value. So we don't need any log factor here if we would be needed, like for storing a map or something like this. And if we had the situation in which c is bigger than this, we probably the first thing we would do is to go through the whole array and just like compress the coordinates, because then we know that the compressed coordinates cannot be bigger than n times m. Okay, but we don't have to do it. So this is like very naive approach. A little more clever approach would be to calculate the answer. If you have a calculate the answer for one square, we can just move this square to the next, like one position to the right, and we can just add one column and remove one column from the square. So if we are updating like counters for every element, we just need to add some more elements, and we have like k of them, and we need to remove k elements from the counters. So this will ends up in algorithm n times m times k, and unfortunately I think that some teams have this kind of algorithm and pass the time limits. Am I correct or not? There are some teams with such an algorithm? Okay. Okay, but looking from the but it was not. It shouldn't pass the time limits. So maybe it depends on in what order you are going through the array. So it looks like the. I try to be like a little bit generous with the time limits. So maybe you just pass it because of it, but it's not an intended solution here. So it shouldn't pass. What we are looking here is a real solution which is in times linear of the size of the array. So we will be aiming for this kind of solution. Okay. So in order to get to this solution, okay, I will just erase this part. Okay. So what we will do in our approach, we will try to do something like this. We will try to move a square from left to the right. And we will be adding a new column, but actually adding a new column will cost us the time proportional to k. But we will be updating more than one square at a time. So actually, what we will be doing, we will be updating k squares at all. So let's say that we are interested in k squares, which are like on top of each other, and we will be moving all of these k squares to the next column. And we will do this in such a way that like the time complexity of movement is all k, but we will be updating k squares at the same time. So so this will so this will gives us a speed up. And actually, to do this, first we will consider a little bit easier case when n, so the number of rows, is no bigger than 2 times k. So we will consider this case first when we so then actually we only have like k plus 1 different squares possible here. So the picture will be as follows. So let's say that here we have 2 times k, and let's say what happens with we have some square, and let's fix one particular value c. So let's fix one particular value c, and let's see when this value appears in the square. So probably, so first of all, we are only interested in the values which appears in this in columns which are covered by the square. So we can have some values here. We can have some values here, and maybe we have some values inside of square, and we would like to know when we have some value inside of the square. So actually, we can divide our strip in 2 parts of size k, and for each part we will store only one interesting number. So for elements which are in the upper part, we will store the maximal row in which some element of C appears. So let's say that we have some element C, and here we are interested in the maximal row. So for instance, this will be max row or value C, because this is like the element C, which is the which is the lowest. And so maybe let's look at this example. And for the lower strip, we will be interested in the mean row of some element of value C, which appears in the lower strip, and it is the highest element. Okay, so if we have this number, max row and mean row, can we say when this square, and we can move this square up and down, because as we say before, we will be considering this the squares which are like which have the same x position but different y positions. So when such a square contains element C, okay, so for the max row, we are only considering values C which are in the upper strip. Okay, so and we are interested in the lowest row in which this element appears. So actually, we know that here this lowest row. So here we don't have C, no C in this part. Okay, and for the mean row, it's symmetric things. We only considering the guys which are in the lower strip. So this is the place where we have no C. Okay, so it turned out that from this values of max row and mean row, we actually can calculate which squares are good and which squares are not good. Okay? Can you see how to do this? Okay, so maybe let's first look at max row C. So if so for instance, if the square, the top side of the square is in the same row as max row, then it will have the element C inside. Okay? So what if this square is a little bit higher? Yes. Okay. So this element will be if the square is here, like on this height, and if we move the square up, it will still contains this element C, because this square will be like the height of this upper strip is the same as the size of the square. So if let's say y is the like the height, like the row in which we have upper side of a square. So if y is smaller or equal than max row, then we know that elements there's some element C in the square. Okay, can we do something similar with the mean row? Okay, so what will be the So basically the bottom side will be like I plus k minus 1, something like this. And if this is like greater or equal than mean row, then we will also have a element C inside. Okay, and are there any cases in which we have element C? Okay, so okay, so max row is equal to what? Okay, max row is equal to 0. So this is mean like is the first element or there? Okay, okay. So if it's one indexed, so this means that we don't have any element of C in the upper strip. Yes. Okay, and okay, and in mean row is equal to what? N plus 1. Okay, so that means that we have no element C in the whole range. Okay, so then it means that we have no element C in the square. Okay, but okay, but this means that no these inequalities do not hold. Okay, so these are we are interested in inequalities which holds when we have some element C in the square. So actually this is an example when these do not hold, so this is still consistent with what we have. So the idea is, okay, we have these inequalities. If one of them is satisfied, we have some element C. The question is it everything? So can we have some example in which these equalities are not satisfied and we still have some element C? Okay, and the answer is no, because when we look at the square here, so if we have some elements in the upper strip, and if we put a square here. So actually, in order of, if we want this square to not have any of the elements in the upper strip, it needs to not have this lower element. Because this is like, if we are moving the square downwards, the last element will, this will be the last element which will be removed from the square. So actually, these are the only two inequalities which says when element C is in the square. And actually, this is pretty interesting what we have here, because this, if we like consider only one square, like these equalities can test for one square whether it contains C or not, but we can do this in other methods. But this is interesting because it allows us to look at all possible positions of the squares, and these positions which contain C are pretty we have only two segments of these positions which are interesting. Okay, so either Y is like, if we consider every possible position Y for the top side of the square, so either I is less than max or C, so either Y is this in this range, or I is greater than mean row C, and we have to like do something minus K plus 1. So we have two ranges of good positions of the square. Of course, we also have cases in which either one of these range is empty, then we have only one range, or both of these ranges are like, or the whole range is possible. But then, but what we are saying here, we have at most two segments where we can place our square. Okay, so basically we can maintain like we can maintain a big array, let's say of size n times m, and in which in this array we will be storing the counters for every possible square. So, for instance, if this square is located here, so this will be, so in this, so actually this array is a little bit smaller. It's like n minus k plus 1, m minus k plus 1, to store all of the squares. So if we know that the possible placement of the square in which x is here and y is in this range and this in this range, so we know that for these squares there's a c here, and we will be like treating every possible value separately. So we know that we can put plus 1 in some. We can put plus 1 in some two segments in our array. Okay, so so once again, if we do it like naively, like if we put plus 1 for in every cell here, we will gain nothing. But the thing is that we can do some, we can be more clever, and we don't have to like put plus 1 in every position. We can use of the fact that we will do some post-processing using prefix sums. So basically, if you have this problem in which you have to like put plus 1s in some segments, but you are not doing any queries in the meantime, so you can do like post-processing. So instead of like putting plus 1 to the whole segment, you just put plus 1 in the beginning, you put minus 1 at the end, And later, if you do this for all of the segments you would like to have in this array, later you will just do prefix sums. So if you encounter +1, then you will be counting this +1 for every cell until you reach -1, and that will mean that you are canceling this +1. So we will do prefix sum at the end of the program as a post-processing. So thanks to that, we can update such ranges in a constant time. So what we will do here, what we want here. So basically, if we have this max row in min row for every possible value, we know how to calculate in which squares this value is. So one important question is, what will happen if we move our block in which we are looking for the squares one step to the right? So then we will have to recalculate all the min rows and all the max rows for all the possible values of C. But fortunately, we only need to do this for these values of C which are changing. Okay, and which values of C are changing? Okay, we are introducing some new values here in this row, in this column. So here we have new values, and we are removing some values from this column. So old values. So here we have old values to remove, and here we have some new values to add or to insert. Okay, so we can look. So let's once again consider only specific value of C. So this specific value of C maybe it appears somewhere in this new column, maybe it appeared somewhere here in this old column. So we have to insert these new values of C and remove these values of C and update max row and min column. Okay, so what data structure allows us to inserting elements, removing elements, and then report the maximal or minimal element in the structure? It's a min q or max q. So once again, we look at this. These insertions and removals are not like any insertion or removals. We only inserting from the one side, and we are removing from the other side. So we just making a sliding window here, and we are adding elements from one side, we are removing elements from the second side. So actually for every value of C, we will have a min q which will store the value for values of C in the lower strip, and we will have the max q for values in the upper strip. So every time we add some new elements or remove some elements, we can update this max row and min row in constant time. So this is one part. So we can move and we can update max row and min row in constant time. That means that here we are adding 2k elements, and here we are removing 2k elements. That means that we can make update in time O of k. So as we mentioned here before, we will be doing the update in time O of k, but we are doing this update in order to get information about all of the squares which are in this strip of size 2k, and there are k of them. All right, but this is still not the end of the update, because the update has two parts. First of all, we need to update max row and min row. But the second part is actually updating these ranges here in the array. And the problem with this update is if we do it again, like for every strip once more, we need to like consider every possible value of C, which is in the which can be inside the squares, and for each possible value of C, we will do some, we will do another segments. But the problem is we cannot consider all of them. So we only so here for the Q's we only considered the values which were changed. So the values which were introduced, all the values which were removed. So the problem is we cannot do, we don't have time to do anything for the values which were not changed. But if the value C was not changed, then the range, these two segments for value C, will also not change. Okay, so basically, if the value C is not changed, then the strips, these segments here, will be exactly the same. So, so we would like to get this get this for free. And basically, what we can do here, we will just make another prefix sums. But then here we do some prefix sums in the like in the vertical direction. Here we will do some prefix sums in the horizontal direction. So basically, what is happening here, we will not only add +1s to the vertical segments, we will add +1s to the whole rectangles. And this is pretty much the same. We can add +1 to the one row of the to the lowest left coordinate of the rectangle. Here we would add -1, and here we would add -1, and here we would add +1. And if we do prefix sums over this coordinate, over this in this direction, and then in this direction, the whole squared will be will have 1s inside, and in the fields which are not in this rectangle, we will have 0s. So basically, this means that we can do this +1 -1 thing when this rectangle starts, and then when it finishes, we can put -1 and +1. So as long as these two segments do not change, then we do nothing, and we only do work when they change. If the segments change because some value C was introduced or removed, so we change the value of max row and min row in this process, then we need to close the current rectangles we have. So we need to put -1 and +1 for these rectangles in order to close them, and then we will open the new rectangles which have the new values of max row and min row, and then we will make +1s and -1s for these new rectangles. And that means that we can do this update in constant time for every value which change, and for value which does not change, we don't have to do anything. So this is really update of this process is proportional to k. Okay, and this is almost everything we have in this problem. So we can solve this problem in linear time on the size of the board, but we did one simplification at the beginning. We did a simplification that our board is of the like it has height of at most 2 of the k, because if the height is smaller, then this the same algorithm applies. Yes, because it doesn't really matter if it's smaller. The thing is, one thing which we used here is that if we have a square of size k, either the square is we can like divide this strip into 2 strips, and either this square intersects the upper strip or this square intersects the lower strip. So if the whole strip is even smaller than 2k, still the same algorithm holds. Okay, so what happens if this square is higher? I mean, what if n is greater than 2 times k? Yes. So this is the idea we have here. So actually, if our rectangle is higher than 2 times k, we can just partition it into strips of size 2 times k, and basically what we'll do here, we will just take every possible strip of size 2k, and we will just, so we can take like the first strip of size 2k, and then we can move it lower to consider the other cases. So in order to consider so this will be given like the answer for this square. If we would like to get the answer for the lower squares, we need to consider one more strip of size 2k, but which is located k rows lower. So we will partition our whole rectangle into the strips of size 2k, but we will have each strip will start at some the first strip will start at row 0, the second strip at row k, the third strip at row 2 times k, and so on. So basically what we'll have here, we will have n divided by k strips, and in every strip we have to make an amount of work equals to m, because this is the length of the strip, and for every like placement in the length, we need to make the update in times of k. So this is the total complexity of the solution, which results to n times m. Okay, so that's it, and we have another I think interesting problem which needed our min use and max use. So this is only also useful to get them into use, and okay. So that's pretty much it. Thank you very much.